So welcome to the lecture on automatic control system. Today we will discuss in this lecture about Laplace transform and transfer function. So in previous lecture we saw that in the design process of a control system we need to make block diagrams, and those block diagrams contain transfer function, and to calculate the transfer function we need to use the Laplace transform. So yesterday we saw that the block diagram can be represented here as input, output, and here is the transfer function. So to find the transfer function we need to use the Laplace transform, because Laplace transform is a technique that can be used to convert the differential equations or integral differential equations in time domain to algebraic equations in complex frequency domain. So when we have to solve a differential equation, we can take the Laplace transform. We can shift our time domain to S domain. S is the complex frequency domain, and then we can come back by taking inverse Laplace from S domain to time domain, and we get the solution of that differential equation. So Laplace transform is defined. So here Fs is defined as integral 0 if there is some function ft e power minus st dt. So here this is a function ft, that is the time domain function, and we are getting here function fs, that is the Laplace transform of ft, and this is in complex frequency domain. The inverse Laplace transform is also available. So if we have a function in S domain, we can take the inverse Laplace and we can get the time domain. So here we can see that the inverse Laplace transform it gives the ft, and that is 1 by 2 pi j integral c minus j omega c plus j omega fs e power st ds. So here there are several functions in time domain, and there are already available formula that we must know, because we can use them directly if there is some such function in differential equations. So for example, we have the Laplace transform of here a unity function 1 is 1 by s. The Laplace transform of exponential function e power at is 1 by s minus a, and Laplace transform of sine function sine at is a by s square plus a square. Laplace transform of cos at is s upon s square plus a square, and here the Laplace transform of t sine at is 2as upon s square plus a square whole square. Laplace transform of t cos at is s square minus a square upon s square plus a square whole square. Now here we can see that the Laplace transform of sine bt into exponential function, that is e power at. So we are getting b upon s minus a square plus b square. So here we should note one point, that if we have sine bt, so the sine bt, the Laplace transform of sine bt is b upon s square plus b square. However, if we take the Laplace transform of sine bt into exponential at, so it will be b upon s minus a whole square plus b square. So here whenever exponential function like e power at is multiplied, simply we can, the Laplace transform will be s minus the s minus a of like this. So similarly, if we have Laplace transform of cos bt equal to s upon s square plus b square, so Laplace transform of e power at into cos bt equal to s minus a upon s minus a whole square plus b square. So only we have to subtract this coefficient a to the s and we will get the Laplace transform of e power at. So Laplace transform of t power n upon factorial n is 1 by s n plus 1. Now we come to the more applicable system like differential equations. So because differential equations are used widely, and so we should see how we can take the Laplace transform of differential equations. So here we can see that the Laplace transform of ft, where ft is a differential equation, ft is a function, and so Laplace transform of ft is fs, then Laplace transform of the nth derivative of ft, that is Sn into Laplace transform of ft minus Sn minus 1 f0 minus Sn minus 2 f dash 0 minus fn minus 1 0. So this is the nth derivative of ft and we are taking the Laplace transform. So for example, if we want the first derivative like L d by dt ft, so it is equal to, so n is 1, so it is s and L ft minus f0. So L ft is fs, so we can write s fs minus f0. So if L ft equal to fs, so L d by dt ft, so this is the first derivative of this ft, that is equal to s fs minus f0. So this is the Laplace transform of the first order differential equation. And similarly we can find the Laplace transform of the second order or higher order differential equations. Similarly, we have the Laplace transform for the integral equations. So here we can see the Laplace transform of nth integral of ft. So we can see 1 by s n Laplace transform of ft plus fn minus 1 0 by sn plus fn minus 2 0 upon sn. So here is, we are seeing these functions at the initial conditions at t equal to 0 plus fn 0 by s. So these are the initial conditions at time t equal to 0. So if we have n equal to 1, so the first derivative, we take the first integral, so 0 to t ft. So this is the first integral of ft. So here we are getting 1 by s L f t plus f dash 0 by s. So L integral f t 0 to t. So it is 1 by s f s minus f dash 0 by s. So this we see that we can find the Laplace transform of differential and integral equations, because any system can be represented by differential equations. When we model, mathematical models are given in terms of differential equations, and we can take the Laplace transform of these differential equations, and we can enter from time domain to the S domain, complex frequency domain. And then these equations from differential equations, they convert to algebraic equation, and we can solve these algebraic equations, we can factorize, we can simplify, and then we can take inverse Laplace and we can come back to the time domain. Now, as I told that the objective of the Laplace transform is to use in the to find the transfer function. So now we will discuss what is transfer function. So we represented a block diagram. We represented a system or a subsystem through a block diagram. A block diagram is a block that takes the input. So it takes some input and it gives some output, because every system in physical any physical system that comprises with many subsystems, and we give some specific input to the system, and that input it passed to the subsystems. So each subsystem has some input and then output, and that output works as input to the next system. So any system we can represent our subsystem with input output relationship. This is block diagram. And here inside this is the transfer function. So these transfer functions they characterize the input output relationship of any system. So input output relationship is characterized through the transfer function, and these transfer functions are valid only for linear system, time invariant system. So the system should be linear and time invariant. So the differential equations that represent the system should be linear, and that should not vary with time. The parameters should not vary with time of that system. So the transfer function we can define. Transfer function is defined for a linear time invariant system, and it is defined as the ratio of Laplace transform of the output to the Laplace transform of the input under the assumptions that all initial conditions are 0. So suppose I have a system here and Rs is Laplace transform of input and Cs is Laplace transform of output. So the transfer function Gs is Laplace transform of output upon Laplace transform of input. Now we saw that when we do the Laplace transform, there are several terms that contain the values at initial conditions like time t equal to 0. So those conditions we have to assume 0 when we perform the Laplace transform of these functions. So let's take, if we can represent a differential equation of nth order So here I am writing the differential equation of general differential equation, and in this differential equation we have yt is the output and xt is the input. So this is the so it is this case. So we have in time domain, this is input and here is the output, and here is some function. Now we know that if we want to find the transfer function, we need x, s and y, s, because we need to go in s domain. So we can take the Laplace transform of this equation and we should try to find ys by xs, because that will give you the transfer function for this general equation, differential equation. So we take the Laplace transform. So we know that the Laplace transform of nth order differential equation is s power n fs plus some terms that contain initial condition. We can again see the formula, we can recall the formula. We can see here the d by dt n, dn by dt n for ft equal to s power n, and this is the Laplace transform of ft, and minus these terms Sn minus 1 f0 minus Sn minus 2 f dash 0 minus Fn minus 1 0. So we see that except this function Sn Lft, all the other functions they take the initial conditions, their values is defined at the initial condition, and in the definition of the transfer function we already said that the initial conditions should be 0. So we all these terms except the first term will be 0. So the differential the Laplace transform of dn by dtn ft equal to Sn and Lft, and Lft is Fs. So we have Sn into Fs. So here we can write a n into s n f s. So here we say y s because here our function is y t, so we say y s. Now we come to the next one. So this is a differential term with n minus 1th order. So here we will have s n minus 1 y s plus a1. Then here the first order, so s y s plus a0, and this is y t, so its Laplace transform is y s, and this is equal to, similarly this side, the input side, the differential equation to the input side is b m, here s power m xs plus b m minus 1 s m minus 1 xs plus b1 s xs plus b0 xs. Now we can take it ys outside, so we will have ys and here a n s n plus a n minus 1 s n minus 1 plus a1 s plus a0 . So here we have bm sm plus bm minus 1 s m minus 1 plus b1 s plus b0 and xs. So now we have to find the Laplace transform gs, and gs is ys by xs. So here ys by xs is equal to bm sm plus bm minus 1 sm minus 1 plus b1 s plus b0 upon this term. So an sn plus a n minus 1 s n minus 1 plus a1 s plus a0. So this is the transfer function for these general differential equations. So we can see that in this differential equation output part is nth order as well as input is also nth order. So we learn how to find the transfer function from nth order differential equation, and if we have some equation of finite order, let us say second order differential equation, third order differential equation, we can use the similar process and we can find the differential of that differential equation, we can find the transfer function. So for example, we take one example. So we have a equation like dct by dt plus 2 ct equal to rt. So this is the first order differential equation, and we have to find the Laplace transform. So from this equation, it is clear that this is the input and this is the output. So, we take the Laplace transform of both sides with assuming all in initial conditions 0. So, here it is S into Cs, because this is the first order differential equations. So, S power n, so S power 1, that is S, and Ct we have Cs plus 2 Cs equal to Rs. Here capital letters we represent the Laplace transform function, and here in small letters we represent usually in time domain. So, from here we have to find, so it is like we have input Rs and here output Cs, we have to find Gs. So, Gs equal to Cs output by input. So, here we take Cs S plus 2 equal to Rs. So, here Cs by Rs equal to 1 by S plus 2, and this is the transfer function Gs of the system. So, that is how we can find the transfer function of differential equation. Now, there is some properties of transfer function. You see, here is input, here is output, and this is the block. You know that this block represents the system, and so this block is made of system parameters. It represents the system property. Therefore, the transfer function is a property of the system, and it is independent of the input. It does not depend on the input. This output will depend on the input as well as the system property, that is the transfer function. But this transfer function is the system itself, its own property. Now, second point is that seeing a transfer function, we can't tell the physical structure of the system, because several different physical systems may have the similar transfer function. And second point is that the denominator of the transfer function will tell us the order of the system. So, the highest power of S in the denominator will tell the power of the, whether it is a, like here S power 1. So, this is the first order system, and this we can also know from the this differential equation, that this differential equation is the first order differential equation. So, the system is of first order. This also we can get from just looking at transfer function. The power of S, the maximum power of the highest power of S will decide the order of the system. And the last thing we should note that the transfer function is defined only for linear time invariant system. It is not defined for nonlinear system or systems that vary with time, like we have missiles, rockets. So, there is variation in time, the mass of that system. So, the transfer function is not defined for that. So, I would like to stop here, and some examples that we took from the reference books of Norman S. Nice and K. Ogata. So, I would like to stop here, and I thank you for this lecture. See you in the next lecture.